Push That Rock with Simpson Math. Lesson on limits. Let's look at a piecewise function. That is a function that has more than one rule. So this one has two rules, two pieces, so to speak. It has a rule for when x is positive, when x is greater than 0, and a rule for when x is negative, when x is less than 0. Notice it does not have a rule for when x is equal to 0. That means that 0 is not in the domain of this function. We want to look at the limit of the function. We're talking limits here. And in particular, we want to see the limit as x goes to 0 from the right. So I drew a little number line here to help us with this notation. The way you read this is you say x approaches 0 from the right. So that superscript plus you always read as from the right. So here's 0, we go to the right, and we're picking numbers over here that are closing in on 0. So I'm going to think about inputs like 1. Now I'm going to get closer to 0. I'm going to approach 0. So maybe a half, and then a tenth, and so forth. And I would keep doing that. And what I'm interested in are what are the outputs doing? What are the outputs doing as the x values get closer to 0? What are the y values getting close to? Well, the y values are always 1 bigger than the input. See, the input plus 1. So 1 turns into 2, a half turns into 1 1/2, or 1 5/10, and a tenth turns into 1 1/10, and so forth. And we can see that the outputs are going to get ever closer to 1, so the limit is 1. There's a very technical definition for this. Here's the definition. I'll state it out loud. For every, this symbol means for every, proximity measure. We'll use epsilon to represent proximity measure. For every positive number that serves as a proximity measure, there exists another positive number such that, this pen is dying, such that when x is within delta units, I chose delta for the number that must exist for every epsilon, of a, so a is this value that x is approaching, so we read it, the limit of f of x as x goes to a in general. So in our case, in our specific example, we have 0 here. It guarantees that the distance between the function and the limit, in our case our limit is 1, is less than epsilon. So notice if somebody chooses epsilon to be a tenth, well then delta could be anything smaller than a tenth, because when we get smaller than a tenth, we're always going to be within a tenth of 1, because any number I pick after a tenth here, we're going to be less than a tenth from 1. So if I pick 1/20th, well, you add 1/20th to 1, you get 1.05. So notice I'm less than a tenth from the function. The output is less than a tenth from 1, because I'm 5/100ths from 1. So this you don't have to worry about so much in a lot of the problems. You can figure out what the limit is by just carefully thinking about what the outputs are approaching as the inputs approach the given a value. Now, since we did a right-sided limit, we should do a left-sided limit. So here's another one-sided limit because it has a superscript. This time it has a negative superscript. So the way you read this is x goes to 0 from the left. And remember, the rule was that the outputs are always 2. So I'm going to pick x values that are to the left of 0, like -1 is to the left, and I'm going to get closer to 0, so like a -10th and a -100th. Well, the outputs are always 2. So what do we think the limit is? It's a little too obvious. It's going to be 2 because, that pen is fine. It's always going to be 2. Now we can graph this function. So the function, remember, should not have a dot anywhere on the y-axis because the input of 0 doesn't have an output. There's no rule for when x is 0. But we learned that there's a couple of limits at 0. From the left, the limit was 2. So if this is 2, from when we come from the left, the limit should be approaching 0, 2. And the function is always 2 for negative values, so we just have a flat line here. Then we have a linear function with a slope of 1 that should cross at 1, except that it doesn't touch the y-axis, so the y-intercept is not really relevant here. But anyway, it has a slope of 1, but we know that the limit, as x goes to 0 from the right, the limit of the function is 1. So the function's coming to this 0, 1 point right here. So we have a line. Hopefully I made it slope. Well, I missed it a little bit. Okay. So I didn't make it quite steep enough. But anyway, we have a slope of up 1 over 1 for all the positive values. Now these two open points here represent a limit. Now the limit doesn't have to be an open point. It's just that on this particular function, there is no value, so we can't have a closed point. So this open point is for the limit as x goes to 0 from the right. We see that the function is headed towards 1. But if we come from the left, what are the function values approaching? Well, they're approaching 2. So the limit as we go to 0 from the left, the limit of the function will be 2. Well, what about the limit itself? Just the limit, not one-sided, not from the right, not from the left, just as x goes to 0. Well, anytime that the one-sided limits are not the same number, the limit doesn't exist. Because you can't meet, and there's that dying pin again, you can't meet the definition for any proximity measure. You can't find a value that when you get that close to the, in this case, 0 value, you will be within that proximity measure. So, for instance, if somebody says you must be within a half a unit of 1 to be convinced that the limit is 1, well, notice from this side, there's no way we'll ever be within a half a unit from 1. We're always going to be a full unit away from 1 coming from the left. And then coming from the right, we're always going to be a full unit away from 2. So it's not 1 and it's not 2, well, then it's not anything. There's no limit. Math made simple. Simpson math.